And I'll just, actually, I overheard Matt's conversation here, so I will repeat a few things that Matt just said here, hopefully for everyone, because I thought I was actually thinking of doing this before. So the next couple of hours, we're going to try to get very practical in our use of Python. In a somewhat semi-realistic way, we're going to do a little bit more, something that looks a little bit more like software engineering, maybe, to begin with, looking at the idea of software testing and why that's a good idea in a scientific context. And then we're going to really get quite practical in giving you an example of what could be a scientific workflow that you could use in sort of semi-realistic context with some data and some analysis and how you put those together. Maybe trying to integrate things into something that looks like a day in your life, my life. But before I go into the material, just a few kind of side comments about Python in the scientific context. One thing is one of the reasons that we teach Python in these workshops is that it is a very easy language to learn and teach from. It was actually designed originally as a teaching language, right? A language to teach people how to program. And so the emphasis in Python is on fairly easy to read code that doesn't have a lot of, people hear of code in other languages, a lot of languages that are sort of compiled languages rather than interpreted languages have a lot of decorations around code itself, and Python is sort of bare. It just has the bare minimum what you need to perform the operations. So that's one reason to teach Python. The other is that there is a growing ecosystem of projects around Python in science to do a variety of things that you might want to do. So, with the basic tools that we teach here on how to do very simple things in Python, you can now go out and find other people who have done much more complicated things in Python. I'll point out one of or a few of the kind of major projects. One is SciPy. So I encourage you to go to scipy.org. SciPy is a very large set of libraries that are sort of collected together to do a whole bunch of things that you might want to do. Optimization, Fourier transforms, integration of functions, interpolations, things that scientists need. So this gives these tools. And a lot of SciPy is actually relies on an underlying layer of old, venerable Fortran and C codes, BLAS and LAPACK, and these things that have been developing over many years. So it's an interface to those things scientists use routinely. There are other. So if you just Google, there are a lot of libraries to do whatever. I don't know. So I'm just gonna pick on someone. What is kind of an operation that you do every day, or an algorithm that you need? I don't know. Support vector machine, right? If you just do this, you'll fall on some implementation of a support vector, right? So just try that with your favorite algorithm or whatever favorite computational operation that you need to do, and it's likely that you'll fall on somebody's implementation, and some of these will be really good. This happens to be, for example, very good. Scikit-learn is a very good machine learning library, Python, which I use every day. So I knew I was going to find that. And then similarly, there are other things. So I don't exactly know what each one does, but I recommend. And a lot of these things. Yet another reason for Python. It's open source. It's free. A lot of these libraries are open source and free. Very good for reproducibility of our results. And with that, let's go on to reproducibility. So if you go to the website again and you go to our current slot, software validation and testing, and click on that, that will take you to this page. And this has two parts. We'll start the first part, unit testing. So what we'll talk about now is the concept of unit testing and how to build sort of standalone scripts how to go from what you've seen in the notebook into standalone scripts that you can start building your own libraries of routines, of algorithms, and test those routines and algorithms to see that they work. So the idea here is that software is another tool in our toolkit as scientists. So we have instruments that measure things, and we have instruments that we use to analyze our data. And software is one of these tools that we use to analyze our data. And much in the same way that we would not use scales that aren't calibrated to measure how much of a reagent we put into an experiment, or you wouldn't use some, in my case, some magnetic resonance imaging device that isn't calibrated to measure MRI images. We don't want to use software that isn't calibrated in a sense. And our calibration is simply a set of other software routines that look at our software and test whether that software is doing what it's supposed to be doing. And so the idea is usually the kind of data that we'll deal with is going to be fairly complicated. The data sets that we deal with are going to be fairly complicated. And the main principle behind software testing is that we want to be able to derive a result by hand, sort of look at our data, at a very simple example of our data, derive a result by calculation with pencil and paper, and verify that that calculation comes out of our software as well for this simplified data set before we go on to a very complex data set and start getting numbers out of that without even knowing if those numbers are the correct numbers. And the idea is to have a test suite for our entire library of functions that is easy to run, runs very quickly, and can verify that the functions. Now, a typical thing that might happen is that as we go along and write more and more code, functions change. We have to rewrite certain functions to do more than we thought they would do initially. That's often referred to as refactoring. You take a piece of code and you kind of try to rewrite it so that it still does what it's supposed to. And when you do that, you can always go back and run the code to see that it still derives the result that you expected. That gives you a little bit of peace of mind. I imagine people here who've written code in scientific context, you have this thing where you wrote a piece of code, it does some analysis, and now you want it to do something more, and you kind of keep your fingers crossed that it still does what it's supposed to do in that earlier context, and you hope that you haven't just broken it. And this is just a formal way for you to verify so that it does what it's supposed to do, and it still does what it's supposed to do if it changes. Okay, with that, let's take a very simple example. So down here in this unit testing example, there is a little function. Let me just copy over this code. And what I'm going to do is I'm going to use some text editor. This is actually not my personal favorite text editor. It's just a text editor that's free and available. And I'd recommend, if you don't yet have a favorite text editor that you use on a daily basis, find a powerful text editor. Text Wrangler is one that's good. TextMate is also good on the Mac. Matt likes VI, I believe, or Vim. I like Emacs. There are a variety of text editors, but it's if you work with code, a text editor, adopting a text editor that you like is a good thing because you'll spend a lot of time using it. So I'm just going to use this one because it's fairly simple. It's there. And I'm going to copy over the code into here. So I just pasted this code in here. And what I'm going to do is I'm going to save this file. And I encourage you to follow along. Let's save it as a .py file. And we'll save it. I'll put it in my home directory in a new folder called testing. Called this insights. So I'm just doing this. I'll explain the code in just a minute. There we go. Okay. So one nice thing that a good text editor will do for you is that it will highlight certain elements in the code. So for example, we know that import is this kind of a special name in Python, and it gets this blue. The function definition def is also sort of a special name that gets highlighted as well. It makes it easier to read this code and understand. So let's look at what this code does. This code starts by importing a module from matplotlib. This is the same library that we used for plotting, also has a bunch of utility functions inside of this matplotlib.ml. We import that as ML, and then we import numpy as NP. The next thing that happens here is just a function definition. A function called getSightings, and that takes a file name as input and a focus animal. Now, what are we doing here? We're going to analyze a CSV file. You can get that CSV file right on this link here. So I'm going to get this CSV file, and I'm going to move the CSV file into my testing directory. I'm just going to put it right here. Right? And let me open this file. I'll open it in whatever, yeah, it's already open, in whatever is the default program to open CSV files on my system. It's Excel. Okay, so here it's a table. And what this table has is a series of animal sightings. So, okay, imagine this is the kind of scientific data we're dealing with here. Researchers have been sitting out in the field on these days, April 22nd and 23rd, 2011. And they recorded the sightings of certain kinds of animals, owls, foxes, musk oxes. And whenever they cited that, they put down the time and also how many of these animals were cited at that. Okay. So that's simple math. And then, so what this function does is it starts by using a utility function called csv_to_rec, which will read in from the file, from the CSV file, from this comma-separated value file, into a table. And then, so, okay, let's break this down by doing this in a notebook. So let me go into testing. Now let me open an IPython notebook right here. IPython notebook right in this directory. Okay. So I'm going to do this a little bit in the opposite way of what I usually do, but the logic still applies. I'm importing these in here. Okay, so I ran this cell that has this first thing. And then let's say that I have file name. I have my file name equals mean sightings. No. Sightings tab. So notice that I'm being very lazy here and pressing the tab as early as I can to complete this, and IPython will do that for me. Okay. Okay, so what happens when I call this line here? Okay, what is tab? So tab is this special kind of NumPy array called a rec array, or a record array. It's an array that contains records. So what is record? So for example, if I look at item 0 here, it has 2 items of kind date time, which are times, right? So this is the first. These are the first 2 columns of this table are the date and the time. Those are represented here and here. And then I have a string and a number. So that's pretty much the first record, the first line in this table. Notice that this record array has a d-type. If you remember from previously, the arrays have some d-type, and usually it would be something like a float or an integer. These kind of arrays have special d-type that contains the name of the column, right? So the name is taken from the file here. The name of the column, and also what type that name is. So these are objects, this is a string, and this is an integer. An 8-bit integer. And one of the nice things about these record arrays is that you can index them by the d-type, right? So that's what happens here in this function. Here we are indexing into this array by the animal, right? So these are the animals. These are the records of the animal column in this table. Owl, fox, musk. Okay. And so what happens here is that the focus animal, we derive out the indices or the Boolean array. For example, if my focus animal was owl, I would derive out a mask, true, false, false, true, false. That would give me, so now if I do tab in these indices, I get back the records for which the animal is owl. Okay, so that's the operation that happens here. And that allows us to then count how many, right here, I'm counting how many animals were viewed in this focus animal, and that then returns the number of records, the number of lines that had that animal, and the mean count. Here I'm just taking the mean of the counts in everything. Okay? So this is what this function does for us. We give it a file with these records, we give it a name of an animal, it will give us back how many records are there for this animal, and the average count in those records. Okay? So now we want to go and ask whether this function works properly. Right? It looks like it works properly, but when imagine situations in which there are some corner cases that we haven't thought about in which this function might not. So we want to thoroughly test this. Okay, the way we do that is, so now I've kind of as an aside, I've demonstrated how you might make a library of your own functions, right? So this file is now a library of my own functions, and I can in fact, since this notebook is in the same directory as this .py file, I can go and now the way I add a cell into this notebook is Control-MA. It's a bunch of keyboard shortcuts. You can get them here. So Control-A inserts a cell above. That's the shortcut I just used. In this cell, I can do import mean sightings. So mean sightings, the way Python works is if you are in a directory, if your PWD or present working directory is a directory that contains a .py file, one of these Python files, you can try to import the module that is that file's name. So now I have mean sightings. What is that? It's a module. And if I do dot and ask to tab complete, it will tell me what are the things that module contains. So it contains the things that I've imported, ML and NP, right? Because I've imported those here, right? These are these names. But it also includes a function that I've defined, get sightings. And I can ask, so I open a parentheses and hit tab to get the help documentation for this function. And it says, alas, no docstring, which is not a good thing. So let's go and write a docstring. When you define a function, you might want to tell us what it does. In this case, get data from animal sightings file. And I write down what are the inputs for this thing. The parameters are a file name. That's a string. The file containing a table of animal sightings, and focus animal is also a string. Oops, sorry. I'm not so used to this text editor, so I'm doing the name of the animal family. And then it returns total recs, the number of records for this animal, and mean count, average, individual count for this animal. Okay? So it's good practice when you define functions to properly document them like this with the doc string. The main reason for that is that you yourself, 6 months from now, will look back at this code and wonder what it's supposed to do and what are the inputs, what the inputs mean, what the outputs mean. And if you do this immediately when you write the function, you will have this fresh in your mind. 6 months from now, you'll probably forget what you wanted to do here. Okay, so now what I can do is I can, the important thing is if I hit import again, nothing has changed, still no doc string. So the trick here is that you need to reload the module. What Python will do is if you've imported a name like mean sightings and you ask to import it again, it'll usually be lazy. It'll say, oh, I've already imported this. I'm just going to use, I have this name already. No need to re-import it. Unless I explicitly tell Python, oh, I want you to reload that module from the file. Reloading that. Typo. Undent does not match outer indent. Let's try that. Okay, success. That was something about white space. It happened. Okay, so now when I open a parenthesis and hit tab, oh, there it is. The doc string that I just wrote, okay? Another way to get the doc string is to type a question mark and hit enter. That'll open a little window at the bottom, and that'll also open the doc string. That can work for my own functions, but Control-MA adding another cell above, that works also for, say, NumPy functions. Here's the NumPy A-range help doc string. Another nice trick is that if you put another question mark here, so double question mark, and hit Shift-Enter, it'll actually open the code. Here's the code that I just down there. Okay, I can open it in another window by hitting this pager. So here is the full code that I have in there in that file. And that's very useful if you're using some function and you wonder, okay, what is it doing? You can go and look at the code without even knowing where the code is saved on the file system. All right. So now I think, okay, so we have mean sightings, get sightings that I've imported. Say I have the file name that I'm using, file name, here it is, and say owl. Here we go. So this is the result that we get. It's a tuple. 2 records of owls with a mean sightings of 17. Let's look, does that make sense? Well, there's 14 here and 20 here. So 34 divided by 2, I can do that without even a pencil and paper. Yes, the mean count is 17, and there are 2 records in this file. Okay, this is a very simplified data set. Imagine that you had now a data set with hundreds of these from many different researchers doing these kind of sightings, or you had a, I don't know, file with 100,000 different locations that you measured in somebody's brain, or whatever measurements you do with time series. It would be very hard to calculate by hand. So we take a simplified data set. This is a simplified data set and test that. Okay, how do we actually test it? So we do something similar to what we just did in the notebook, but we're going to do this formally inside of a file. Okay, here's our testing file. We'll call it test mean sightings. So I'm starting a new file here, and in that file I copy these lines from mean sightings import get sightings and file name I have. So notice these are lines that I actually had in my notebook. I didn't quite have from mean sightings import get sightings. Here I'm just importing just the function. But I had something similar in my note as well. So I'm following the same logic of my informal testing in the notebook to do the formal testing. Test mean sightings. Okay. Now we're going to copy this cell here, and I'll explain what that does. This defines a test function. Okay? The testing mechanism that we're going to use is a library called nose. It's another Python library. And nose, the way that nose works is it looks for files that contain test underscore in the beginning of them. And it'll run those files. And inside of these files, it will look for test functions, functions that start with test underscore, and it will run those functions. If those functions all run cleanly, and we'll define cleanly in just a minute, then the test works. Okay, and it says everything's fine. If they don't run cleanly, then there's a problem, and it'll flag that problem. Okay, so let's see how that works. I just defined the test function by getting the OWL sightings, and now I'm asserting that the number of OWL records should be 2, and if not, then the number of records for OWL is wrong. Otherwise, I might assert that the mean OWL count is 17, or the mean sightings for OWL. Yes?
If mean sightings wasn't the same direction.
If mean sightings. If this thing was not in the same directory.
Yeah, would you have to? But I'm assuming that that's like kind of opening up mean sightings.py and function.
Yeah. This has to be in the same directory for now.
Right.
Let's talk later about how you could do this other way. For now, let's just assume it does.
Okay.
It's a bit complicated.
This is another Python code that's in the same directory as mean sightings.
Yes, this is another function called test mean sightings that is placed in the same exact directory. So you'll see I saved it right next door.
Okay.
Right. This is where I saved mean sightings, and I save test mean sightings in the same location.
So the code is opening up mean sightings, extracting out get.
Exactly. What this does is it opens mean sightings. In a way, it opens mean sightings and it imports get sightings from it. Now get sightings is a name in this function, and we can call it like this.
Right.
Okay. So if I do this in a notebook, it's the same principle. If I do this in the notebook right here, now I have get sightings in here. I can pretty much run this piece of code here. Oops, there we go. Okay, so now I have owl rec is now defined in here. It's 2, and owl mean is 17. Now let's see what happens when I run this piece of code. Well, nothing happened because it's true. That's part of the. So assert is this kind of statement that just passes by quietly if everything's okay, and will raise an assertion error if nothing is okay. So if I just change this from assert that owlrec equals 3, which is a wrong statement. So if this little bit here is wrong, the way the assert is structured, it's got assert, then some logical statement, and then some error of, I should say, a comma, importantly, and then some error statement that would be thrown. So let's see what happens when I run this like that. I get an assertion error, and I get the error message, number of records per owl. Okay? So that's exactly what is going to happen inside of this function. It's going to try these assertions. If no error is raised, the nose is happy and everything gets tested. Let's see how that works. I go back to the terminal, and I change my working directory into testing, and now I run a little program called nose tests. And what nose tests does is it runs the code inside of this test function, and it tells me I run one test, it took this much time, and everything is okay. Right? Let's see what happens if I change, and I insert this error, 3, in here. Well, in that case, it will say, this test failed. There's one failure. I ran one test. This is the failure, and it will also actually present to me the error message that assertion raised, which is number of records per owl. Now I fixed it. Now everything's okay. All right, and that is the logic of testing. So, as it says here, we calculated the correct values for these by hand and inserted those. You might imagine that you have some calculation, some more complicated calculation of some algorithm that you're trying to implement, and you know that it has some particular special cases where you know exactly the value. Those are the values that you would insert there. And this is what happened. And now we tried to change the test so that it failed. And that's what we saw. And now it's working. Okay. So now I assume that you've all been following along and have sort of this structure machine. But if you're not, it's time to start making this the structure that you have in the machine. And then we're going to do an exercise. But before we go to the exercise, let's see what questions we have about all this. Do whatever you do with it. Test that it does what you expect it to do. Here I put in real numbers, and I see that whatever my modeling efforts are extracting those data. Right. Sometimes here I read actual data, so I can go to my project and do that. And now it's going, it's analyzing, okay, it failed completely. So now it's going and running, it's, doing, also I'm writing here object-oriented code, comparing results, and here I'm also comparing to some results that I've saved in the file. Yeah. And sometimes it'll be very hard to write tests, but it's a good thing because now I'm pretty sure, and this is a complicated set of code, there are thousands of lines of code in there. I don't want to break it while I'm working, so I can always go back. So okay, here's the solution to the problem. Okay, let me kind of reiterate a little bit to help get people on track and also move on and show you the solution to this. So, I may have confused you a little bit by going to the notebook. We are leaving the notebook behind. We're not going to use the notebook anymore. I used the notebook only to show you step by step what happens. So close the notebooks. We are now only working in a text editor and with the terminal. Okay? As Matt mentioned yesterday, Python has several different modes of operation. There is a Python interpreter that can take Py files and run them. So you can take the test mean sightings file and run it like this. I just ran that file for mean sightings. Okay, so Python is a program that will interpret .py files for you. It is also an interactive interpreter that you can run in the terminal, right? So here I am in a Python interpreter. A equals 1, print A, and I can exit now. Okay? And it also gets run when I do nose tests in here. It gets run, it does certain things, it knows what to do. So nose test is a program that calls the Python interpreter to run the test functions on functions. And so what we're trying to show here is how you would realistically run programs that are written inside a text editor, not inside a notebook. Now, the structure of the logic of what we're doing is that we're defining functions that we'll want to use inside of this function, inside of this file, mean sightings. In there, we're writing just functions. In this case, some function that does some analysis on some data. Inside of test mean sightings, we're writing test functions to test those functions that we're defining mean sightings. So, for example, I have this owl testing function. I just copied over because I'm lazy, and I'm going to change this into muskox is correct. And for that, I'm going to rewrite this as muskox. So let's, okay, I'm going to change this also to be muskox, and muskox, and muskox, and muskox. Now let's see this, and here I need to change that as well. So I just copied and pasted it, and I'm just changing everywhere where it says owls. I'm now saying muskox. Okay, now let's see. What do you think will happen when I run the tests now? Anyone have a guess? Will it pass? Will it fail? It will fail. Why will it fail? Because I forgot to change the numbers into the correct numbers. And yes, indeed, the mean sightings for muskox is wrong. It's not 17, so what should it be? Well, I'll just calculate it by hand. 31 plus 20 is 51. Divided by half is 25.5. Is it?
Yeah.
How many records are there? There are 2 records, so that should work. There we go. I forgot to save it, I believe. There we go. Okay, so now it's ran 2 tests. It had 2 functions in there, 2 tests. They ran those 2 tests, and now those tests pass. Okay, so that was exercise number 1. So now we have 2 tests that pass. That was pretty straightforward. There were no, like... Yes?
How does program
floating point numbers. Well, here's a floating point.
Yeah, I just stopped.
Oh, how does it know that the floating point is... do you mean, are you referring to precision issues?
Yeah, like...
Yes. It's a good question. I'm not sure exactly how it does it in this case. Seems to work. I think it does it up to some tolerance, basically. It's possible.
So you're lucky. You should never compare flows for quality.
Yeah.
That's a bad idea. You should really compare for closeness.
Yeah.
Relative error.
Right, so we could have done, instead of this, we could have done this minus that. And the absolute value of this difference is smaller than...
You just got lucky. They have to be exact.
I don't have NumPy here.
You should not count. You never count.
So, okay, for everyone who wasn't following this discussion, when you represent floating points in computers, you can't represent to arbitrary precision. And so when you're comparing 2 floating point numbers, for example, here, the result of that function, mean, and 25.5, those should come out to be the same by calculation, but the representation on the computer, because it's not done to arbitrary resolution, it's done to some limited resolution, might yield some really, really small difference between them. So they won't be exactly equal, they'll just be, the difference between them will be very, very small. And so here instead of testing that they really, really are equal, what I've done here is I've taken the difference between them, I take the absolute value of that difference, and I say, that has to be smaller than some really small number. Okay? That way I overcome the problem that computers can't represent continuous numbers, real numbers, many are. Or arbitrary. Okay, so yes?
I'm confused. I don't know where nose test is. Where is nose test located in the directory?
It's not there. So if I, to answer your question, which nose tests? Oh, it's a nose tests program that's installed in some bin directory somewhere on my path, on my shell path. So it's just a program like ls or cd. It's another program that's available for the shell.
So how did that get... I just don't understand how that gets incorporated into... Like, you change test mean... You change test mean sightings, you updated this code, and then you put in nose tests and it runs that code.
Yes, nose tests is a program that runs in the shell that we saw yesterday morning. And what nose tests knows is how to run, it looks inside of the directory where you're running it. You run it in a certain location, right? It knows to look in that location for files that have test underscore in their name.
Okay.
It takes those files and it runs through Python the functions in those files that have test underscore in their function name.
So Okay.
And if one of those if this raises an error, it says, oh, that was a test failure. It counts those. And if it doesn't, then it just says, oh, that test must pass. I'll show you something.
I understand that aspect. I got lost with, where you're just putting those tests in the terminal.
Okay, yeah, note this is just a program that we have installed on our machines. Because you installed Canopy, one of the things that Canopy, among the many things that Canopy installs on your machine, is this program, nose tests, that gets installed.
I mean, we could just run test mean sightings PY, right?
Yes, we could have done this. The problem with that is that all this does, that's an important distinction, is it just goes and runs these test definitions. And the tests themselves never get, right? These tests, so what happens when I do that, these tests get defined, but they don't actually get run. They don't get called.
I mean, we could, modify this so that it would do that, right?
Okay.
I mean, not that, I don't want to,
Yeah, I mean, we could have done this, right? Test owl is correct. Down here. Oops, sorry. Right, like that. Now I run it, and it actually got called in there. But nose is just it's a good framework to work with, because it counts how many tests you're running. It doesn't just raise an error. So let me show you. Okay, let's say that I insert an error here. So I'll do what you suggested. I call the function in there, you see? So now, when I run this Python test mean sightings, it actually gets called. Now let's insert an error here. The problem with that is that this will raise an error and everything will just grind to a halt. It will not, if I had also in here test muskox is correct, it will not get to run the muskox is correct test. It will raise an error and then it'll just stop. And knows what it does is it sees the error, it says, it's fine, there's an error, I'm just going to count that error, and it moves on. It moves on to run all the other tests as well. So it gives you some convenience. Okay?
I mean, it seems like that you wouldn't have to, that the assert command or function is ending the program, and if you use something else like an if statement, print statement, then
sure, you can do print statements if you want debugging. That's all fine, but it's not as efficient as using.
Okay, I just
because then you have to go and look and see. You have to read a bunch of print statements telling you everything is fine, everything is fine, everything is fine, or if something went wrong here in this line. Nose tests just kind of does that.
The basic idea is, if you were to do all this by hand, you will effectively rewrite nose, right? Because you'll be writing all these print statements and if statements and checking for asserts and all this kind of business. Or we can just have a library that does it, and we can just use a library that already does it. And in one case, you have to do a lot of work, and in one case, you don't have to do a lot of work.
Just put these assert statements, and it'll do all that, all those print statements.
You originally have to write it. Incorporate it. That's right. Like, it's just you don't have to remember what the code was called. You just run this.
Yes. I think if I understand your question,
understand how.
Yeah, let's just move on. It becomes a little bit philosophical here. So, okay. So far, we've tested this function on some pretty generic just results as they come out. Now we want to test something which is more of corner cases that might occur. For example, what happens if at some point in time you're trying to analyze this, you're looking at some data file, and the animal is not actually present. You're looking for an animal that isn't present. So now we're going to try to test a bit of more kind of a corner case. So here is the function definition for the test for this corner case. Right, I'm inserting here. I'm calling this on the same file with an animal called not present. Right, that's not a. And what I'm saying is when that happens, well, the number of records is 0, and the mean count should be 0 as well, right? This is the expected behavior. This is the behavior I expect to get from this function under these conditions. Okay, let's run those tests with that. Okay, so it doesn't currently do that. It doesn't return the expected behavior. That's not because this test is wrong. This test is actually the behavior we expect it to have. The problem is the function doesn't do what it's supposed to do in these conditions. So we have to go and fix our function. Yes, we have to go and fix our function to do that. Okay. So let's work on this together. What do we have to change here in order to get the right answer? Where's the problem here? Can you guess it? Okay. We could one thing we could do to debug this is use print statements as suggested. Let's see what answer did come back in the test. Right, we know that the answer was incorrect, but we don't quite know what it was. So let's just insert a print statement right in. And then when we run those tests, it has an unexpected indent because I don't know how to use this editor. There we go. Okay. So what happened is it returned 0 for the first thing, right? So the number of records is indeed 0, but then the mean that was returned in nan, which is the representation of not a number. And the issue here is that this particular corner case goes into here and it inserts a non-input in here. Because there are no records, there are no rows in that file that have not present as an animal, this mean calculation will be evaluated to a not a number, which is not what we want. We want to get a 0 back. Okay? So we have to fix the function. What suggestions how to fix the function? We could test for nanhood. Yes, we could do this. If np.isNan, which is a function that tests whether something is a nan, mean count.
First you know to be 0, you can.
We could say mean count equals 0, right? If it comes out, evaluates to nan, what we actually mean is a 0. Well, what's the problem with that? What kind of problems would you expect to get with this particular solution? Okay. The general problem, I think, is that you might get a nan here for more than one reason. Right? It might be the case that you get a nan because one of the inputs to one of the rows, for example, contains, instead of a number, it contains something that is not a number in it, and that produces a nan. In which case you get 0 there, even though you're supposed to get some number. So it would. I think this is a little bit fragile because it would return nan in more than just one situation, and we want to deal only with one particular situation. So I I'm against that. Although it would have worked for this case. Let's just show that it would have worked for this case. So it is. So here we're testing that. I did insert an error here before, so let's fix that one. Okay. So that worked. Okay, so it is a solution to this particular problem, but I think it would also, we'd get caught up in other errors because, yeah.
You have to specify the data type.
Data type.
Like you said, if number or string. You said, like, if you, instead of having like an NaN, you have like a string. I mean, it has to be greater than 0, right?
Which has to be greater than 0? What exactly?
Well, the count, right?
Count. Well, no. Here there are no counts because there are no rows in the table. We get when we do this tab count is focus. We get back nothing, a none.
Right.
So that's
take the NP mean, you get an error. Right?
So when it's not an error, we get a nan back.
Oh,
that's the problem. So I mean, I think the solution, the kind of canonical solution here, is to explicitly test if total rex is 0. Then just set mean count to 0. Leave that. That would solve. Right, that's how we wanted the function to behave. Is if the total number of records is 0, define the mean count also, and that also passes.
You do a search for the animal. Say you have like tab animal looking for sheep game. Then we do. Is there like a search? Like, or it'd be like column rotating.
This does that.
They have to say
I mean, this focus here, just to kind of give you a little bit more of what is happening here. This focus here, this is going to be a mask with trues and falses for where the animal is, and it's going to return. In this case, it's going to return all falses.
Right.
So I could check for that.
Yeah, if it's false.
Yeah. This is what that does, right? When this sums those trues and falses, it basically counts how many are true. And so total rex is going to be 0 if all of these come out to be false. That's logic, and that's what we're testing. Okay. So that tests that. Okay. So we did exercise 2. Okay, here's another special case. All of the animal names in the data sets are capitalized, right? Notice that here we have all of these are written in a certain way, but as you all know from looking at real data, sometimes data is pretty dirty. And for example, somebody might call this function with this argument. So here, the next exercise is to write a test function that will pass only if your function returns the correct answer files, even if the input argument focus animal is set to. So the input that the function gets is incorrectly capitalized. First of all, run that and see that it currently fails. Okay, so this will fail right now. So start by writing the test, see that it fails, and then go and fix the behavior of the function so that it actually passes. Okay. So there's a hint there about capitalization. Let me just show what we mean by this hint. So I'm opening a Python interpreter in my terminal now. Let's say I have a string that has as its value this thing, which is our incorrect input. This string has a method which is available to us like this, capitalized. Okay, this is how it's called. It's not that you can't do this, capitalize, right? Because capitalize is not a function that Python knows. Instead, it is a method of the strings like that. Okay. So let's see how we did this. Let's see someone kind of walk through what they did. Any volunteers done this? You have a green sticky. Go ahead. What did you do?
Oh, okay. So I just add a line right before that's the.
Oh, but that's not the order you were supposed to.
Oh.
Let's write the test first.
Oh, okay. I didn't.
Okay. It says in the exercise, write the test function that will pass only if your function is correct. You've solved out of your problem. Okay, let's do the order you were supposed to do. Let's call this test something, robust to input. Okay, so now our input is is not capitalized like this. Okay, that was the definition of the problem. We have an input which is sort of funky, and now we want to be able to basically run this with that input and get the same result that we would if the input was actually the right one. We replace this here with this funky input instead, and that's the test. And now let's see that it actually fails. Okay, so it fails. Well, actually, this is ow. Right, so it says this is wrong. Okay, and now to the solution. So now we've defined a new condition for this function, and this is very typical for, I think, for my own workflow as a scientist. Is I write some function, it does something. Now I come across some new kind of data, and I try to put that data in, and I hold my fingers crossed that it will give correct result. But in this case, it would not have given me a correct result. The result that I would have gotten would have been 0, and that would have surprised me as a scientist, and I wouldn't have known where that comes from unless I had written tests to tell me where that comes from. Okay, so let's solve the problem. What was the solution?
So add a line right before each line, right? Put like focus animal. Focus animal. Dot generalize.
And of course, if you don't have typos in your code, then it passes. Okay, so this is what is called test-driven development. It is we usually, when we do this, or so far when we've done this, we've thought in this order. We have a function, and now let's come up with ideas about how to test it. But actually, the way we should be thinking about it is that we write the function for a particular purpose. The function is supposed to do something. So if we can specify in advance what the function should do for a given input, we can write the test and then write the function. Okay, that's called test-driven development, and is kind of a neat idea because you can think of the test as being the spec for your function, right? It's like a contract between you and the data. It's like, if you give me this data, I will give you these results. And then you go and you have to actually solve the problem of making your tests pass, right? You have to write the algorithm, you have to write the code that goes and makes your tests pass. So your goal is to make the tests pass, rather than making the tests a secondary thing, sort of an adjunct thing that you just do to check that everything's okay. This is your calibration. So your calibration always has to be correct.
I find it interesting that you set the capitalization requirement for focus animal, and then you get the variables, and afterward, instead of like getting the variables and capitalizing it. That just saves time. You see, like if you look at the mean sightings full the script.
This one.
Yeah. See, you capitalize first. You specify the capitalization, and then when it's reading it in, it just automatically changes the capitalization, right?
I'm not sure, but it sounds like an implementation detail, so maybe let's not stop.
No, I'm just wondering if what this does. Say you have your CSV file and it's reading it, or your tab file, whatever, and you say focus animal equals that, and you're reading it in. Does it change the like it's going through Al and the?
No, there's only one. It's just a string input that's being capitalized. It's an implementation. Let's move on. So okay. Now here's a case that often happens, which is you're working on a big project and you have all these functions that do all kinds of analysis, and now you've come up with a clever new way to do one of these things. Let's say you thought up an implementation that's faster. Or in this case, you want to give the code you want to share your code with another colleague who wouldn't necessarily follow on all the implementation details that we have here. We have all these clever indexing tricks and stuff like that from NumPy. So we can rewrite the function to be much simpler. Right? So here is another implementation that is supposed to do the same thing. It's supposed to give us the same result, but the code is quite different. Look at it. It's got quite different. Of course, it does the same thing with the capitalization, but instead of doing these indexes, instead of using indexing, it actually loops through all the records and counts the number of records and number of animals, and then calculates your mean by dividing total count by total recs, and then returns the number of records and animals equal. So now what you can do is you can replace your code without replacing the tests, and the code should still, the test should still run just fine. I mean, usually you do it in the opposite direction. You start with something simple and clunky, like this. Right here, there's looping, and looping takes more time than operations on arrays. So you would go and you write something that passes the test like this, which you understand completely. And then what usually happens to me is I'm trying to optimize my code to be faster, and I start adding to it all kinds of indexing tricks and array tricks, and I still want the tests to keep on passing. That's called refactoring. Basically, the code changes, but it's supposed to get the same inputs and provide the same outputs. So the tests ensure that happens. So what we can do is we can just take this entire piece of code and just replace our original code. So okay, let's just do that. Here we go. Okay, so I just replaced all this code by this other piece of code, and it looks pretty good. Should work. Let's run the tests and see what happens. Oh no! So there's one failure and one error that happens, right? So code that looks like it's supposed to do exactly the same thing apparently doesn't. So, and this is called regression. So regression is, you run the code, can be a situation, and I have tests like these in my project where you run the code, you get some results, you save those results, and assuming those results are correct, you test that that's the result. You test that those are the numbers that you get every time you run the tests. In the future, when you upgrade some piece of software on your machine, you want to see that that upgrade didn't change, say, the result of some analysis. In this case, we're changing the code itself, and now we have a regression in the sense that a test that used to pass no longer passes. Okay, we changed the code, and now it doesn't work anymore. Okay, so we are shocked to discover that 2 of the 4 tests now failed, and how can that be? Okay, so let's together maybe analyze this issue and try to think what caused this regression to happen. Any ideas? Why is this new piece of code that's written here failing with tests that previously passed? In particular, test animal not present are tests that when an animal is not present, we give back 0 and 0 is failing, and the test that the muskox is correct is now failing. So, yeah.
Because it's not saving a specific number of records for each animal.
Okay.
Right? So that's why the code's wrong, because it's like each animal doesn't have a total recs, right?
Well, the code is not always incorrect, I should point out. Right? Test owl is correct, still passes. That's part of what's nice about nose, is it ran all the tests. And you can see these dots here. Each one of these dots here is a test case. So there are test cases that still work. It's just that this test case and this test case doesn't work. This test case for the owl works just fine still. So it's something slightly more subtle than just the code generally does. The code is okay.
No, yeah, I mean, it's because it has the total recs is the same for all the animals, right?
No, it goes for record and tab. It counts. If the record animal equals the focus animal, it adds a 1 to that total recs. Otherwise, it doesn't. So it does count how many lines in the file have that animal.
Oh, I just didn't know if it. Okay.
Yeah, that's what it does. It goes record by record, line by line in the file. If that line has as its animal the focus animal, it adds 1 to total recs. It starts with 0, and then it counts.
Is it going through each?
It goes through every line in the table, and if the animal in that line is the focus animal, it adds 1 to total recs. And if it's not, it doesn't. So that seems okay. And like I said, it works for it does work for the owls fine. Right? It wouldn't if it wasn't counting records, it wouldn't work for the owl. It is counting.
So it goes. So it's going through each animal. I just don't see the four for each focus animal.
But focus animal is just the stringing here.
Okay.
It's just a single string. It's just owl or muskox or something like that. You know?
I see. I just get cited.
Yeah. That's here. This name of the animal that.
Yeah. Okay, that's what. Okay.
Yeah, it is.
Just don't guess what is the error. We just see the box.
This error is just the fact that in Python, if you try to divide by 0, it raises an error. It's not going to give you a meaningful answer. Instead, it raises an error because you can't divide. Fine. So the problem is we're dividing by 0. Okay, so that's a hint for why this is not working. And specifically, when the animal is not present, as before, what's going to happen is that total recs, right? It's going to go through this loop, and total recs is going to stay 0, right? So we can't actually do this division if total recs is 0. So we can fix that by doing something like if total recs equals 0, then mean count equals 0 as well. Else, do the division. Okay? So that might help avoid. So if total recs is 0, it would never go in here, and it would never do the division by 0. And oops. Yes, equals is comparison, equals assignment. I get that all the time, unfortunately. It's just something. Okay, so that did solve that problem. Okay, so we're no longer dividing by 0. That solved the first problem. What about the second problem? Mean sightings for muskox. Wrong. What do you think is going on here? Yes, that's a good idea. Okay, so let's print. You know what? Let's do that in the test. So I think that the best practice is to go and do that right here. Print musk ox rec musk ox meat. Okay. Let's run that again. 2 and 25. It is again, you saw that yesterday, you may remember this. Integer division in Python returns integers. And the correct result here should be 25.5, which is not an integer. So the problem with this particular case is that we're dividing here counts by recs, and both of these are integers. Find them to be integers. So that will not work unless we do something to make this work. One way to solve this problem is to do what's called casting, is to turn one of these into a float. All right, division of an integer by a float is going to be a float. Float being a floating point number. So that's a way to get floats from the integer. That here might actually just solve the problem. Yes? Okay, so that solves the problem. Okay? So this particular example just demonstrates the situation that you undoubtedly come across, which is that you write something, it looks like it's correct, and then your tests that previously passed now no longer pass. And you know, I think probably in a lot of science that happens all the time and happens silently without us having any idea why or how it happens until like 3 weeks later we look at the plots and they're all they don't look like they looked a month ago. I'm sure you all know the situation. Made some changes, you're not so sure what part of the changes did what. And I think the idea behind this particular session was if you have very fine-grained tests of small parts of your code, you can gain control over what it is that changes and how that affects the outcomes of running the analysis. There's a whole little bit here about test-driven development. So I mentioned this before. Test-driven development is the idea that you start by writing tests, and then you go and refactor your code. The extreme case for that is that if we started off with the test for the owl case, we could have started out with the owl case, right? The first test that we had in here was this test mean sightings, test owl is correct, which tested that the owl rec was 2 and the owl mean was 17. We could have written that first, and then so let's see if I can comment out quickly. Comment out. Let's do extreme test-driven development here. Going to comment out the entire function also.
Is there a function like comment here to here?
There probably is, but I don't know this text editor well enough to actually do that. I know how to do that in Emacs. Yeah, that's. I was asked before why people are so obsessed about their text editors. This would take me like a second in Emacs. Here I apologize. Okay, so now this fails. But the extreme case of this is to say return 217. Oops. Right, so now I have a function that for this particular, it passes this particular test, right? Beautifully, right? I've written the function that fulfills this. And sometimes we do this in, sometimes you do that in your analysis. I know what the answer should be. Okay, I'll write in the answer in my analysis. Sort of give me the right answer. But then as you go along, the requirements become more complicated, right? If we add this second test, there's no way that this particular function, return 217, will pass both of these tests together. And it's at this point that we need to start actually writing code that passes for both conditions. Right? If our only condition was pass the OWL test on this data, then we didn't need any more than just return 217. So this kind of flips the whole development process a little bit on its head and says, go and write the tests first. Write the minimal amount of code that will pass your test, then write another test, and then change your code so that it passes both of these tests, and then keep going changing the requirements to be more and more complicated, and changing the code, of course, to pass it.
How did you do that? You made a lot of pound signs to just erase it really fast.
Oh, I did undo. Command Z. I just undid all that.
I thought there was just some trick to slide pound signs. Take them out.
No, I don't actually know how to work with this text editor. Okay. So, with that, the next kind of step that we're going to take. So let's see first. Do you have questions about testing, just the general and test-driven development? Yes. The bonus part of the exercise was to make this pass for another file. Oh, if the file doesn't exist. Really? Exercise 3. What if the file does not exist? What your function should return? Okay, let's do that. Okay, let's do that together. Right. What your function should return if the user gives the function a file that does not exist? Aha. Okay, so what do you want the function to return? Let's write the test. Okay. I'm just going to delete these pounds here. Okay, so now I'm back here. I have all these tests that I've written before, and everything passes. Okay. So next I'm gonna let's make the function more functional by making it robust to a file name that doesn't exist. So okay, def test file not here. Okay. So now the file name is some nonsense. Is not here .csv. And the question is, what do we want it to return as output when that happens?
Mr. Daniel Hawk right here.
Sorry, animrec anim mean equals get sightings sorry, with some animal. Let's say with owl is the animal. Okay. So what do we want to return here?
Error method saying that.
Oh, error. That's complicated. Okay, but doable. No, more complicated. Let's just say that it returns none and none. I wonder if this will work. Well, you know, let's be even. Let's go easy on here. -1. Okay, if the file doesn't exist, return -1. Then we'll know that that's. Okay, so here we wrote the test now. Okay, if the file is a file that's not there, we should return -1s. Instead, what happens when I run the tests, it raises no such file or directory. It raises an error. Okay, so what should we do to make this test pass? So we need to go and change the function itself to recognize files that aren't there. And in order to do that, we need, okay, so let's see if Google is our friend. How do I check if a file exists in Python using Python? Without using a try, let's not talk about try statements. Try is not the solution here. Here is the solution that I like. Okay, so there's a module, a library in Python called OS, which interacts with your operating system. And you can import a submodule called os.path. I'll just do that. Import OS. Okay, I import that. And then I can, up front, I can ask if os.path.exists file name. But I actually want to do that with a logical not in front of this, right? So os.path.exists will return true if that file exists and false if that file doesn't exist. So if not that, return -1, -1, which is what we want to return. Woo! Of course, if you have a tendency to misspell everything, you're right. Okay, so now that passes. Okay, so that's the way to check for the existence of files. Probably answer that question in a roundabout. Okay, that's how you would go along and improve your function, make it more robust. Okay, let's see. What other questions do people have at this point about testing? Okay, so we have another 20 minutes left for this session, and I would like to go to sort of the next step, which is to show you how you could make your Python functions standalone functions that you can run from the command line, like programs. Okay, and we'll do that using this same functions that we've been using so far. So first, let's just demonstrate that we can run this function, mean sightings, from the command line and get meaningful results. I'll do that by basically running this file. I'll just add a few lines at the bottom to give the function its inputs. Right? So what I've done here is to the same file where I've defined the function, I now add a few lines. I define the file name, I define the focus item, and then I run get sightings, the function that's defined just above, and I print the output. And that can be run from the command line using Python mean sightings, like that. Okay, and here it got printed out. So the sequence of events that happens is the Python interpreter sees this, it runs the code line by line, it imports, it then defines the function, it defines these inputs to the function, and then runs the functions and prints the output. And that can be done by calling it from the command line. Okay. But of course, it would be much more useful if we could define those inputs without editing this file on the command line. Right, so consider yesterday you saw the shell, you saw some of these programs have inputs that you can give to it. Git, for example, you can give it a file name to commit. Right, you wouldn't want to go and edit some file somewhere every time you wanted to commit something. In a similar manner, maybe you want to be able to flexibly provide inputs to this function. And the way that's done is that there is another module called sys, which we will now import. And sys sort of interacts with the system, has a particular variable called argv, here defined. Argv is pretty much the arguments that you provided on the command line are a list. So let's print argv here for you. Let's print it before we print the output. I'm just running this. See, it's a list, and it has the arguments that were provided to Python. So in this case, the argument was just the name of the function. But if I were to write here, say this, now it added mean sightings, and it has 0 here as well, you see? Because I just put it here. I think we can arbitrarily make this as long and complicated as you want. And we'll keep adding that. Okay, so this is a useful variable because it's inside our program. That variable is defined inside our program. So we can, instead of hard coding the name of the file, we can say, oh, let's define argv1 to be our file name and argv2 to be our focus animal. And now the way we would run this is we would put the file name first, which is here. And the focus animal is owl. There we go. Now let me print sysargv for you again. Here we go. So this is sysargv. It's a list with mean sightings, and then the sightings tab is the name of the file, and owl as a second input, and it prints out the right thing. I can do that same thing for the muskox, for example, and it will give me the muskox answer. Okay, so this is a way we're sort of moving away from making this hard-coded into making this a program that you can actually call on flexible inputs you provide. Okay? Now, the next step is to make this a little bit more robust, is to actually provide it with what we call a main function. In order to provide it with a main function, we need to add this line. Okay, so now we're adding a little bit more sophistication. We can still call this like, now you can see why I need unit tests, because I invariably will have a typo pretty much any. Of course, I have this. Okay, and this runs it in the same way. Now, what did I do here? What this little block of code here does is it checks whether Python will always have a sort of internal variable called name. And that variable will be set to this value, name, when you call the program from the command line in this way. Right? It will not be set to main if, for example, you import, or you import this. If you import this module, then it will not be set to main. In that case, if you import it, everything will be run in this function except for this block down here. Okay? So this allows this module that we've now written, this file that we've now written, can be used in two different ways. One is it can be imported in some other program, and then the functions that are defined in here can be used in that program. Or it can be run from the command line in this way, and then the main block, the functions will get defined, but also this main block will get run. Okay, so this serves this dual purpose, and that is because we've defined this main block in here. Okay. Now we want to, instead of every time writing Python mean sightings with the inputs, we want to be able to call this exactly like we would call any other program from the command line. Okay, let's see first. Let's stop here and see what kind of questions do people have so far about this main definition and how I've been calling this from the command line. Questions?
Do you know what it is?
Yes. Yes. Okay. The idea is a main function is sort of what will happen, the series of operations that will happen if you call this from the command line, saying Python this file. right? That is the series of operations that will happen in addition to all the other operations, right? I mean, the file itself has just a series of operations. Import this thing, import this other thing, etc. Define this function. And if we didn't have this in here at all, no matter how you ran this function, these operations would also happen. Now, the issue is that you might have two different ways in which you run this function. One is you run it from the command line, like I just did. And the other is you will import this function from somewhere else. When you type import mean sightings, it runs the entire function, except for that block that has, except for that main. That main block will only get run if you run it from the command line. Okay, so it allows this same function to serve dual purpose. You don't have to define these functions somewhere else as well for importing. Okay, the next step is that we want to make this callable like a program. And for that, we have to add this line at the very top. Now, you've seen this line before. Yesterday, at some point, Matt was showing you how to write shell scripts. And the first thing he put at the top was this shebang with the bash program that was going to run that shell script. It's the same thing here. We're just telling it, use this Python. The Python that's defined in user bin end. User bin end is a set of sort of the environment setting. Right? This is you've seen this yesterday at its end. It's the same. It's your environment variables, and one of the environment variables in there might be which Python to use. I don't know if it's explicitly said there. But what it says is, given these environment variables, if I were to type Python at the command line, which Python would you use? So what this line tells the shell is, use the Python that's defined in your given these environment variables. Okay. So, and then the last thing that we need to do is make it executable, right? So if we look at this ls-l, which tells us what the permissions are on this file, it's readable and writable by me, and then it's readable by other people and by my group. But it's not defined to be executable. And what I need to do is I need to change its permissions to be executable. Chmod is changed the permissions on this file, and you can see that it now has the X flag, which makes it executable to myself and anyone else. And now this function is executable by doing / mean sightings and providing the input. So sightings tab sm.csv, the file, and then the name of the animal that I want to run this on. And voila, it runs. Okay, so this is how you take a series of functions that you defined in Python. So now this implies a full chain of a workflow that you might use. You go and you hack on something in a notebook. You have some data and you want to figure out how you're going to analyze this data. You start working in the notebook, you load the data into the notebook, and you start plotting it, you start looking at it, you start deriving all kinds of calculated statistics out of that. When you're happy with what you did in the notebook, you copy all of that into a file. Say, mean sightings in this case. You copied it into the file, you write functions out of it, you've divided it into small units that are functions. You document the functions so that you remember what you did a year from now when you look back at this. This is also a good point in time, right when you did that is a really good point in time to make a git commit of this file. And, of course, you write the tests and commit those as well into your repository. And then now you think maybe you can use this as a program to run on your data you add that main block down at the bottom that uses this Python, a set of Python functions that you've written as a program. You add the shebang up here, change the permissions on the file to make it executable, and now you have actually gone to the point where you have a program in your shell that does the analysis that you want to do, maybe produces some scripts that produces some figures that you want to produce somewhere, and that is actually reproducible, right? You don't have to go back to the notebook and figure out in what order exactly you ran the notebook. It's less hackish, to use the word you used yesterday, and more organized. So now you're moving from this exploratory data analysis mode into a mode where you have something that's reproducible, tested, under version control, reproducible science, in other words. Okay. Yeah. What questions do you have?
I know you touched on it, but I'm still confused about what the if name equals name is exactly. Like, what does that syntax mean?
Okay, here we go. Let's try this. Python. Here we go. So Python has these private variables that have. If you see a variable that has underscore before it and after it, that probably means it's a private variable. And it's when you run Python, the Python interpreter like this, that is defined to be main. When you run Python, trying to think how I would demonstrate when it's not actually main. When you run Python mean settings like that, it's also equal to name is also equal to main. But if you know what I'll do to demonstrate this, let's just print. I'm going to print name right here. Okay, print. And now I'm going to open Python interpreter, and import mean sightings. Instead of executing it, I'm just importing it. And the name then is mean sighting. It's not. The name in this case is not main. It's mean sightings. Right. So what happened is when I called import, it imported this file. It's running this entire thing. It's printing the name right here. Then it goes and defines this get sightings. It checks whether name is equal to main. It sees that it doesn't, and it doesn't run. Does that answer your question?
So it should have been.
There's an internal variable. There's an internal variable that tells you whether you are running this through the Python interpreter or whether you're just importing it.
Okay.
And that allows this function, this file, to serve dual purpose, both as a library of functions that you can import and as a program that you can run.
But that line wasn't really necessary. It's not. It will run just fine without it.
Oh yeah, it will run just fine, but you can't just import it. Every time you import it, it would run the analysis every time you would import it. And maybe that's not what you want. Maybe you want to be able to import it and just use the function somewhere else without running this.
Okay.
So think about you have a library of functions, and you want to import it into the IPython notebook and just use those functions in the notebook to do various things. Maybe you don't want every time that you import it for it to also run the analysis, but you also want to use that same library to sometimes run it as a module as a program on the command. So,
I think I see how that would be.
Yeah. Yes.
Is there a good reference somewhere for how to change version file?
Man, Chmod.
Thanks.
Yeah. Chmod is the permission changing. Or Chmod, I don't know how to pronounce it, but Chmod. Is it good? And this has script. Yeah, it's complicated. I just remember by heart that changing it to 755 usually does what I want it to do because it allows a lot. It allows execution.
Plus,
So I could do gmod plus user X, and that would mean the same thing. So just quickly, I'll just, one thing that I wanted to point out, the second part of this that we haven't gotten to, it's fine, continues what we just did to point out that now you have the tools in your you have the tools to produce a reproducible workflow, like I said. And there are some kind of rules of thumb or tips on how you would actually organize your workflow for it to be really, really reproducible. By reproducible, I mean a very specific thing. I mean, this should be something, a set of files on your computer that encode the entire analysis that goes into that paper that you later on write. Right? You should be able to. I should be able to go into your computer and delete all the results of your analysis and leave you only with your scripts and your data. And you should be able to press one button that would then produce all the figures, all the analysis that then goes into the paper automatically. And so this second part that is also linked to from that same location here contains a little bit of a tip on how you would produce what is referred to here as a complete chain of custody or provenance from the raw data to your finished results in figures using these kind of tools. And it uses the same example that we used for the testing. We don't have time right now, but I definitely encourage you to go through that. There's also a link to this very neat paper from PLOS Computational Biology, which talks about organizing computational biology project. It gives a very specific prescription for how you should organize your directory structure. This is very detailed, and I think different people adopt different versions of this according to preferences. And this talks about a little bit about why you would want to do this, but also on how you would practically implement such a workflow using the tools that we've shown you yesterday.
Like, if somebody didn't like one step in the process, they can just take your work off Git or something, and then say,
yeah, and if you've written it correctly, you will be that person on your next project, right? The idea is if you work so hard to make an analysis, make it usable not only for others, for yourself as well. And importantly, make it reproducible so that the results that you're showing in your papers are results that you can reproduce yourself and others can reproduce, otherwise it makes it meaningful. Okay, so I encourage you to go and look at this. We